Hello friends, welcome back to my YouTube channel. In this video we will be diving into some interesting types of numbers that we haven't studied in schools or university but are asked in job interviews, right? So in our list we have some types of numbers. So let's look at the list of numbers that we are going to learn today. So the first one, we have strong number, and then we have Armstrong number, then we have Fibonacci sequence, and then we have perfect numbers, and finally we have happy numbers. We will end our video with happy numbers happily. Happy number, right? So now learning these types of numbers might boost your problem solving skill and creativity thinking. So let's get started with the first in our list. So the first one is strong numbers, or we can call factorial numbers as well. Factorial numbers. So now first look at the definition of first strong number, and then we will move to the mathematical expression to represent such strong numbers, and then we will look at some use cases as well. So the definition is, if you take the digits of a number and sum up their factorials, and if you end up with the number itself, then it's called a strong number. So let me first write down the definition of the strong number. It is a number in which the sum of the factorials of its digits equal to the number itself. Okay, sometimes the definition might be confusing. Now I'm going to shrink this sentence to a mathematical representation. So n, if I take a number n, this is equal to summation of I is equal to 1 to k, right? So I is equal to 1 to k means the number of digits that we have in the number, and di factorial, di is the digit, ith digit, right? So where di is the ith digit and k is the number of digits, n is a number. Okay, so now the strong numbers are rare, and the examples we have for strong numbers, we have only 4 strong numbers. They are 1, 2, 145 and 4585. So these are the only strong numbers available in the entire set of numbers, right? So let's look at how it works. Now if I consider 1, and now I have to take the sum of the factorial of each digit. Now since this is a 1 digit number, I can simply take 1 factorial, it gives me 1. So 1 is a strong number. Now again, if I consider the second number that we have as strong number, that is 2, I can write 2 is equal to, I can just take the factorial of 2, that is 2 factorial, which is equal to 2 into 1, which is 2. So again the sum of the factorial of digit has given me the number, the same number, so I can tell 2 is a strong number. Now again I'm going to take 145. So since this is a 3 digit number, right? So I am going to take the sum of the factorial of each digit. So it will give me 1 factorial plus 4 factorial plus 5 factorial. Now 1 factorial is 1, plus 4 factorial is 24, and 5 factorial is 120. So it will give me 145 again. So we can say 145 is a strong number. Why? Because the sum of the each digit has given me the number that we considered. Okay, right. Now I'm going to consider the third example, that is 4585. 4585. So the number of digits that we have in this number is 1 2 3 4 5. So this is a 5-digit number. So I'm going to consider the sum of the factorials of each digit. So that is 4 factorial plus 0 factorial plus 5 factorial plus 8 factorial plus again 5 factorial. So now it is equal to 4 factorial 24 plus 0 factorial 1 plus 5 factorial 45 plus 8 factorial is equal to 4320 plus 45. So if I add all these numbers, I will get 4585 again. So I can conclude that 4585 is a strong number. So in the interviews, if you are asked about these strong numbers, you have to tell a strong number is a number whose sum of the factorials of its digit gives the same number, right? And you can further tell 145 and 4585 are only the non-strong numbers, right? So moving to the second category that we have for our today's video is Armstrong number, or we can give several others name also. So moving to the second type. Okay, so second category is Armstrong number, Armstrong, or we can call narcissistic, or we can even call pluperfect number. Okay, so what are these numbers? Armstrong number, narcissistic number, or pluperfect number? So a number that is equal to the sum of its own digits raised to the power of the number of digits, right? Okay, so let me write down the definition of this Armstrong number here. So a number whose sum of its digits raised to the power of the number of digits is equal to the number itself. Okay, so sometimes the definition might be confusing. Let me shrink this to a mathematical expression. So if I take a number n, then let's say the number of digits is equal to k, I is equal to 1 to k, and we have di, ith digit, and we have to take the power of number of digits, right? So here we have di is equal to ith digit, k is equal to number of digits, and n is our number. Okay, right. So now we will look at some use cases. The first use case is all the numbers from 0 to 9 are Armstrong numbers, right? So the next point is all the numbers 0 to 9 are Armstrong numbers. So if I take 0, okay, now we can just exclude 0 because that won't come. No worries, we can include 0 also. Right. So if I take 0, now 0 is a one digit number. If I take 0 to the power 1, so 0 power 1 is nothing but 0, right? So the sum of the power of the number of digits raised to the power number of digits has given me the number itself. So 0 is an Armstrong number. Armstrong number. This is not Neil Armstrong number. This is Armstrong number we have studied in mathematics, right? Right. Now we can consider 1. Since 1 is a one digit number, 1 power 1 is nothing but 1, right? So again 1 is also another Armstrong number. Now 2 power 1 is 2. Then 3 power 1 is 3, and till 9 power 1 is again 9. So all the numbers from 0 to 9 are Armstrong number. Now we can consider 2-digit numbers. None of the two-digit number is Armstrong because we cannot find any such number that gives the raised to the power of their own digits is not equal to the number of the same number that we are considering, right? So now if I consider 10, now we are going to look at some examples for two-digit numbers. Two-digit numbers. 10 is, now if I consider 10, so since this is a two-digit number, k is equal to 2, right? So 1 power 2, right? This 2 is the k, right? K plus 0 power 2 is equal to 0 power 2 is 0 and 1 power 1 is 1. 1 plus 0 is 1, right? So now if you take the sum of their individual digits raised to the power of number of digits has not given me the number itself. So 10 is not an Armstrong number, right? Again, if I consider 99, so it should have been written as 9 squared plus 9 squared, which is equal to 81 plus 81, it is equal to 162. Again, it is not equal to the number that we considered. So 99 is not an Armstrong number. Okay, so we haven't invented any two-digit Armstrong number, right? So now we will move to the three-digit number, right? So for three-digit number we have some examples. Let's look at them. They are like 153. Now if I consider 153, so now since this is a three-digit number, so the raised to the power 3 should be added, right? So 1 power 3 plus 5 power 3 plus 3 power 3 is equal to 1 plus 5 power 3 is equal to 125 plus 3 power 3 is 27 is equal to 153, right? So now if I consider the sum of the digits raised to the power of number of digits has given me the number that I considered. So 153 is a Armstrong number. And we have some more examples also. Let me write them down over here. 370, 371 and 407 as well, right? So let's look at this 371, check if this is an Armstrong number. So 371 can be written as 3 power 3, since this is a 3-digit number, k is equal to 3, right? So 3 plus 7 power 3 plus 1 power 3 is equal to, you can use your calculator, or otherwise 3 power 3 is 27 plus 7 power 3 7 power 3 is equal to 343 plus 1. So plus 27 plus 1, yeah, I get the same number again, 371. So 371 is an Armstrong number. Again, you can check this number as well, right? And now we will look at a 4-digit number. So an example for 4-digit number as well, right? So the example is 1634. So this can be written as, since k is 4, because this is a 4-digit number, 1 power 4 plus 6 power 4 plus 3 power 4 plus 4 power 4 is equal to 1 plus 6 power 4 1296 plus 81 plus 256. So if I add them, let me add using my calculator, you also can do along with me. 1 plus 1296 plus 81 plus 256 is equal to 1634. Yeah, it has returned me the same value, 1634. So 1634 is also an Armstrong number, right? So hope you have understood the second category as well. Now we will move to the third category that we have in our list, that is Fibonacci sequence, right? So now Fibonacci sequence. Right, so Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones starting from 0 and 1, right? So we are going to construct a recursive formula for this, right? So now recursive formula, let me first write down the definition for this. A series of number, right? So a sequence of numbers or series of numbers where each number is the sum of the two preceding ones, right? So if you want to find the current term in the sequence, now we have to add the previous two digits, right? Or previous two terms, that's all. A series of numbers where each number is the sum of the preceding ones. So now we should have a initial condition or a base case for this kind of recursive formula. So we can start from 1 and 0, right? Starting from 0 and 1. So now we can write down the recursive formula. Recursive formula for Fibonacci sequence. So this is nothing but fn, right? So nth term or function of nth term is equal to fn minus 1 plus fn minus 2, right? So now if I want to find the number that we have here, we have to add the previous two terms, that's all, right? So by adding these two we can get this, right? That's all. So now we will look at what a recursive formula is, right? So a recursive formula is a formula that defines any term in terms of the preceding terms, that's all. For example, if you take factorial formula, right? So n factorial is equal to n into n minus 1 factorial, right? So the current function is dependent on the previous terms, right? So the current term depends on the previous term, that's all. Okay, and we have studied arithmetic sequence formula also. For example, if you take Tn is equal to a plus d into n minus 1. So now if you want to find out the Tn, so it depends on the previous term also, right? So these kind of equations or formula are called recursive formula, right? So that is just an extra information. Now we will just try to construct a Fibonacci sequence, right? So now we can just start from 0 and 1, right? 0, 1, starting from 0 and 1, right? So these are the starting points according to the definition. 0, 1, to find out, so this is nothing but the f0, this is f1. Now to find out f2, we have to find out f2, we have to add f1 plus f0. So that is nothing but 1 plus 0, that is 1. Again it has become 1. Now this is f2. Okay. Now again to find out f3, we have to add. f3 can be computed by adding f2 and f1, right? So f2 is 1 plus 1, that is 2. Again to construct the f4, we have to add. f4 can be computed by adding f3 and f2, that is nothing but 2 plus 1 is equal to 3. Okay, then again these two should be added together to 5, then 5 plus 8 5 plus 3 8, then again 13. By adding these two we can put 13 here, and then by adding these two we can write 21, and by adding these two we can write the next term, that is 34, and so on, right? So this is how a Fibonacci sequence is constructed, right? Fibonacci sequence, right? So the Fibonacci sequence is 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on, right? So by adding these two you can find the next term in the sequence, right? And so on, right? Now the next type of number that we have is palindrome number. Okay, right? So now the third category is palindrome number. I think fourth category. Okay, it doesn't matter, only the content matters, right? Palindrome numbers. Palindrome numbers mean, now palindrome words are the words that read backwards and forward the same, right? So for example, if you take madam, now if you start reading from here, I mean if you read in the direction in which we have written the word, or even if you reverse the order, it will read the same, right? So madam. So now we will just look at palindrome word. So palindrome word are the words that read the same backwards as well, right? So now madam, what else example? Race car, right? So race car, again if you write if you read the backwards, again race car, right? Okay, so they read the same, right? Okay, again we have level. If you read level, now you see again Level, right? So in the backward direction also it reads the same. So these kind of words are called palindrome words. Again we will look at palindrome phrases also, right? Palindrome phrases. What are palindrome phrases? Now if you have phrases and if you read the phrase backwards, leaving the punctuation and spaces, it also should read the same. For example, if you take a man, a plan, a canal, Panama, right? So a man, a plan, a canal, Panama, right? So just leave these spaces and commas and read from the backwards, from the final letter of this phrase. So right, a man, again a plan, again a canal, right? A canal, Panama, right? Again finally Panama, right? So now a man, a plan, a canal, Panama. So this phrase reads the same from the backwards as well if you ignore the space and commas, right? So this is a palindrome phrase. Another example that we have is Abel was I saw Elba, right? And so Abel was I saw Elba, right? So let's try to read it from the final letter of this phrase, Abel, right? So Abel, again, then I should read was, right? Yeah, was, again I is there, I saw Elba, right? So if you ignore these spaces, the backward direction also, from the backward direction also we read the same. So this is a palindrome phrase, right? Okay. Now this is very simple, right? So you might be very familiar with these type of palindrome numbers, that is 121, right? 121, in this direction also 121. So 11311, right? So again this direction also the same, right? So and so on. That's all. Now moving to the next type of number that we have in our list, that is perfect number. The next is perfect number. Right? So the perfect number is a positive integer that is equal to the sum of its proper divisors excluding the number itself, right? So let me write down the definition over here. A positive integer that is equal to the sum of its proper divisors, right? We will have to study what proper divisors are. That is equal to the sum of its proper divisors excluding the number itself, excluding the number itself. Okay, so now we will look at some examples. If I take a 6, now we have to find out the proper divisors of this 5, right? So now if you divide this 6 by a number, it should give me the quotient as an integer, right? So if you divide 6 by 1, it will give me 6. So 1 is a proper divisor of 6. Again, if you divide 6 by 2, it will give me 3. So again 2 is a proper divisor. Again, if you divide 6 by 3, it also will give me an integer number, integer value. So 3 is also a divisor, proper divisor of 6. Again, if you consider 6 by 6, 6 also gives me, the 6 by 6 also give me 1. So this is also a proper divisor. So these are the proper divisors of 6, but we have to exclude this 6 for taking the sum to check if the number is perfect or not. So if you consider 1 plus 2 plus 3, it also give me 6. So here this is 6 is a perfect number according to the definition, right? So the definition says a positive integer, we have to take a positive integer and we have to take the sum of its proper divisors, right? So beforehand we have to find out the proper divisors of the particular of the number that we are considering, right? So again we will look at another example, 28, right? So the proper divisor of 28 are 1, 2, 3 cannot come, 4, yeah, 5 cannot come, 6 also cannot come, 7, 8, 9, no, 10, 4, 11, 12, no, 13, no, 14, yeah, 14, then 28, right? So these are the proper divisors of this 28, but we have to exclude this 28, right? So excluding the number itself. Now if I consider 1 plus 2 plus 4 plus 7 plus 14, it gives me 28. So 28 is a perfect number, right? So you might have already come across perfect square number. Don't confuse with it. Perfect square numbers mean the square of integers, right? So for example, 1 square is equal to 1, 2 square is equal to 4, 3 square is equal to 9. So these are perfect square numbers, right? Okay. Now to find out these perfect numbers, we have a formula, right? Let me introduce that formula to you. So to find out the, if you consider this one, now you might observe that these 6 and 28 are even numbers, right? So now we have some perfect numbers and all the perfect numbers are even. So far we haven't discovered any odd perfect numbers, right? So that is also an important point. Let me write down over here. All perfect numbers are even. No odd perfect, no odd perfect number has been discovered yet. Right? So now we will just introduce the equation to find perfect number. That is, if you take an n, if this n is a perfect number, if it satisfies this equation, right? So n is equal to 2 power p minus 1 into 2 power p minus 1, right? So where p is an integer, excluding 0 and 1. Now by iterating the values for p from 2, we can find out the perfect numbers. So if p is equal to 2, n is equal to 2 power 0 into 2 power 2 minus 1, that is equal to 6. Wait, 2 power p minus 1, 2p minus 1, right? So 4 minus 1, into okay, I'm sorry. So here 2 power p minus 1, right? P minus 1 mean 2 minus 1, 2 power 1, right? So 2 into 3, that is 6, right? So 6 is the first perfect number, and if you substitute p is equal to 3, it will give me n is equal to 2 power 2 power 2 into 2 power 3 minus 1, that is equal to 28. And the next, for example, if I substitute p is equal to 7, 7 can be written as n is equal to 2 power 6 into 2 power 7 minus 1, and using our calculator, 2 power 6 into 2 7 minus 1. So that is equal to 8128, right? So 8128. Now, if you add the proper divisors of 8128 excluding 8128, it will give me 8128, right? So they have already calculated all these things, and they have formulated an equation for us, so that we can easily find out the perfect numbers, right? Okay, now moving to the last in our list, that is happy number. So we can happily wind up this video with happy number. The next one is happy numbers, right? So now a happy number results in 1 when the digits are subjected to sum of the squares of the digit iteratively, right? So now the definition might be confusing for you. Now I will just explain you the process of finding whether a number is happy or not, right? So now what we have to consider is, if I am given a number, I have to take the square of each digit, and then I will result in a number, and then I have to take the sum of squares of the digits of that result, and then I have to continue till I get 1, right? So now I will just take an example. So let me take 19. So 19 can be written as 1 square plus 9 square, right? So I have just taken the sum of the square of each digit of 19. So that is equal to 1 plus 81, that is 82, right? So again 82 should be written as the sum of its square of digit, right? Of each digit. Now 8 square plus 2 square, that is equal to 64 plus 4, 68. Again 6 squared plus 8 squared. I have to continue the process, right? So now this is equal to 6. This is 100 actually, right? 100. So again 100 can be written as 1 square plus 0 square plus 0 square. So that is equal to 1, right? So if I continue this process and ultimately if I get 1, then that is happy number, right? So if I continue the process and ultimately if I get 1, that is called happy number, right? Now we will just see 4, right? So now if I consider 4, so 4 can be written as 4 square is equal to 16, right? So 16 can be written as 1 square plus 6 square, that is equal to 37. Now 37 can be written as 3 square plus 7 square, that is equal to 58, right? Again 58 can be written as 5 square plus 8 square, that is equal to 89. Now again 89 can be written as 8 square plus 9 square, that is equal to 145, right? 145. Again 145 can be written as 1 square plus 4 square plus 5 square, that is equal to 42, right? 42. Again 42 can be written as 4 square plus 2 square, that is equal to 20. right? So 20 can again be written as 2 squared plus 0 squared is equal to 4, right? So now you can see if I repeat this process, it has made a loop, right? So this is a loop, right? So if it ends in loop, or if it does not get the final value as 1, then it is called unhappy. This 4 is unhappy. This is not happy, this is unhappy, right? So now you see here again, if I repeat the process, I will never get 1, right? So this is unhappy. So the thing you should remember is, if you take the sum of squares of digit and continue the process till you get 1, and then this number is called happy number. That's all. So I hope you enjoy this video and learn something new out of this video. So if you like this video, please subscribe to my channel and share with your friends, so that they also can learn something new and ace their interviews, right? So I have just so why I decided to make this video is, I just was watching an interview video on YouTube, and then in the interview, the interviewer threw a question asking what strong number is, right? So that's why I learned these things, and I just wanted to teach you, those who don't know as well. So please subscribe to my channel, honoring my dissemination of knowledge activity, and share with your friends as well. Thank you.